Well, you're a junior leader, so.
Dr. Schultz doesn't need no camera. He is the camera.
All right, so people, it's making you look good here on video.
You always look good.
Today what we're going to do is we're going to move on and learn more about momentum. Like up until today, we've learned about what momentum is and what impulse is and how impulses change momentum, right? That's the idea. Now today we're going to make the connection to why momentum is really important in the big picture, which is that it is conserved, right? And that should not be a surprise because you might have heard about that before, and that you certainly did last night's reading, which you learned about it. What I'd like to do today is to just kind of explore that a little bit. That's going to be the rest of what we do in this unit, is looking at how momentum is conserved and why that's important. It's a big deal, the fact that momentum is conserved. Remember, when energy is conserved, that's a big deal. This will be a big deal too. Okay. So the targets today, I do want you to know the difference between open and closed systems. This is important. We talked about it before. We like closed systems. We like systems where everything is inside, and then things are usually conserved. This will be a lot like energy. Also today, we want to apply momentum conservation to a couple of cases, which I'll show you in just a second. We're going to do explosions and collisions today. It's very dramatic. And you guys are going to make some predictions, and I'm going to give you a chance to practice and test out what you can, test out your stuff, test out your skills. All right? So that's what we shall do. So I want to start off with a demo or two, and I was going to have you write out your predictions. I think I'm just going to skip that and we'll let you talk to each other about it. We're going to do, the first demo we're going to do is an explosion of carts, okay? And by explosion, what I mean is the carts are going to push off of each other. So I have a red cart, and I've got a blue cart, and what I'm going to do is I'm going to mass up the blue cart, okay? So remember these bars, I'm going to set those on there. And then I'm going to make sure that my red cart has that little spring-loaded rod that's all ready to go. So I'm going to push that in, set that down right next to the blue cart. And then in just a minute, I'll pop the button, okay? So I'm going to give you a minute. I'd like you to make two predictions. The first prediction is going to be, when I pop the button, is one of them going to go faster? If so, which one? If not, then no. So that's a prediction you need to make. And secondly, I'm going to ask the question of, does it make a difference the fact that I pushed this rod in and not that rod? Okay? Would you expect to see a different result afterwards? Okay? So I'd like you to take a minute to talk with your partners about those two predictions.
But they both have the same, they both experience the same. That's not what I was saying yesterday. It was like, it's like the same, they both have the same momentum and the same like magnitude. They both experience the same force, just in opposite direction, and like momentum is constant.
That was funny. When I stepped back here, it got real quiet. Let's see this. All right, so let's have quick predictions. How many people predict that the carts will repel with the same speed? That is, they'll move away at the same speed. Okay, nobody. How many people predict that the blue cart is going to move away faster? It'll shoot off to the side faster. Nobody. And how many people are going to predict the red cart? Everybody.
Wow.
Wow, that's unanimous. So either you're all right or you're all wrong. Ah, okay. Does anyone want to be famous and be in this video?
No.
Wait.
Chris, you're very enthusiastic, right? So presenting
I'll interview you later.
Chris Kostefas to do this demonstration. There's your button pusher.
Hi guys.
Back to the YouTube channel.
By the way, this may be posted on my YouTube channel. Are you okay with that?
Yeah.
Oh, you're gonna go.
Oh, can I I'm gonna subscribe to you. I'll subscribe. Good, I go now. Chris, good luck. Thanks.
That was loading up.
And Chris, go ahead and do it one more time, just so that you can see that again.
We should record every class.
No, we shouldn't.
For like people that miss.
That's so much work. That's so much work.
All right, here we go.
Yeah.
Okay, so it looks like you guys were all good on that. All right. Chris, do you want to flip it around so that you've got, let's test the other prediction. Can you flip the cards around?
Let's
Press-
vote first.
No, Chris, the blue card.
No, go up.
Okay, you ready for this? Wait, let's vote first. We know like people's
Yeah,
interests.
so how many people said that it will matter? It'll make a difference, something different is going to happen now. How many people said it will not matter? Okay, so we all agree that it will not matter. So let's see.
Pretty cool.
Okay? And so apparently, what do you think?
Then we're
It
right.
doesn't really matter. All right, thank you, Chris, very much. Nice
Thank
job.
you. Thanks, you guys.
You're welcome, I clap for you.
All right, so what's the reasoning on that? How
I'm gonna
come,
go watch
how
the
come when you do
movie.
the first launch, how come the red goes off at a very high speed? Let's hear from one person here on this. And you got to speak up nice and loud. What's the reasoning, Chris? Chris, I said Chris, but I meant Kevin. Yes.
Well, the blue card has greater mass than the red card, and the least mass will have the greater acceleration.
That sounds totally reasonable. Less mass means less inertia. Less inertia should mean more acceleration. We agree with that?
Yes.
Good.
Newton's second law.
Newton's second law. Okay, now as long as we're talking about Newton's laws and forces, we'll talk about switching the rods. Okay? How come it doesn't matter when I switch the cards around? This is an important part of this. How come it doesn't matter when the red rod pushes out versus the blue rod? Can you quote a law of physics there that would kind of support the fact that it doesn't matter which rod does the pushing? Rob?
Isn't it a reaction? It's an opposite equal reaction, so if the red rod pushes it, if the red rod pushes the blue card, it's gonna have the same force that the blue card has when it pushes the red card.
That's exactly what's going on. So this is action and reaction, this is Newton's third law. Now that's important, right? Because it shouldn't matter. And so whatever force is acting, that force is going to have a very different effect on a low mass. It's going to make the low mass accelerate a lot, and it's going to make less acceleration here. All right, now what about momentum? Okay, how much momentum do the cards have before I launch them, before Chris launched them? How much momentum do they have right now?
Zero.
Zero, because they're not moving. However, when you pop the button, and that happens, they're both moving. So how much momentum do they have? Let's say that they are in the process of moving. How much momentum do they have now?
Shouldn't they be
Equal and opposite.
Because that one has more speed but less mass, and that one has more mass and
All right, more speed, less mass, less speed, more mass, but they both are moving and they both have mass, so they both have momentum. So if they started with zero momentum, how is it possible that they have zero momentum when they're doing that?
They don't have your potential.
When we're moving, they don't have zero.
Individually, they do not. But I think that together, if you look at that system, there is zero momentum. Can anybody explain how that would be? Diane?
Isn't it because the change in momentum has to be consistent?
All right, it has to do with change in momentum, yeah, because they each change momentum. The red gets pushed out this way, the blue gets pushed out that way, going into directions they were never traveling in before. So they definitely change their momentums. Nancy?
Isn't it like what was on the homework last night that like if one loses, like they give the example of energy that the other one gains it, then it's like conservation of the system.
Yeah, the only thing with that, you're getting there. The only thing is that there was no momentum when I began.
it's just stored.
So it wasn't like one card was moving in the beginning and it gave it to another. So nothing, there was no motion at all. And then there was motion with both cards. Ivana?
Is it because they're going on separate ends of the track?
It's because they're going in opposite directions, right? And what do we know about momentum? Is momentum a scalar or a vector? It's a scalar or vector?
Vector.
It's a vector. So what kind of momentum does red have when it goes this way?
Positive.
Positive.
Yeah, what kind of
Negative.
momentum does blue have? Negative?
It's zero.
So they
Yeah.
cancel out.
So they cancel out. Right. That's important. That's a big deal. Positive momentum, negative momentum, cancel. So they give you zero. Question for you. If I said kinetic energies, what's the kinetic energy right now?
Zero.
What's the kinetic energy now? Yeah, did it explode? Is it zero?
No.
No, because kinetic energy is not a vector, it's a scalar. They add up. So that doesn't work the same way. Momentum does work that way though. So the momentums are equal 0 in the system before and after. Okay? Other questions on that? All right, one last demo real quick. Let's do a collision where blue is going to be moving and it's going to run into red and they're going to stick. They can stick. Digley, can you stop talking? And Mohammed. They can stick because there is Velcro on them. So I'm going to put the math cards on here. In just a second, I'm going to have a dramatic collision. I'd like you to talk to the partner for a second. What will happen to the speed after they collide and stick? Talk to your partner.
There's no friction though.
Are we talking about the speed of the red card or the speed of the blue card?
It's like-
They're stuck together.
it's like-
They're the
they're
same.
like-
The speed of the combined pair.
I think it will like move more towards the one's moving towards the blue one. So I think that they'll both stick together and move to the right. But it will be the velocity of both of them together will be less than the velocity.
And challenge to you, personal challenge to you, can you explain your prediction in terms of momentum? Now that we've said something about it.
It's like it's moving this way and then like
Good job, Rafael.
the opposite force like slows it down because there's like
Because it was
mass or something. I haven't I know that it will go to the right together, right? I don't think it'll stop because there's not enough like newtons or like force or like to push it back.
The red one, isn't heavy, like, doesn't have enough mass to stop.
All right, let's do some predictions here. How many people say that after the collision that the objects will move at the same speed as the blue car? Raise your hand. Nobody. How many people say that after the collision the cars will travel at a lower speed than what the blue car started with? And how many people say that after they collide they'll go faster? All right, so the class is agreeing that they should slow down. Let's do a quick test on this. Anyone want to come up, quickly show it? Chance.
Who wants to volunteer?
Kevin, come on up. You're in.
Hey guys, welcome back to my YouTube channel.
Yeah, don't go crazy. Nice.
Next Minecraft game.
Let's try that again.
Oh yeah, it would be equal.
Kevin, throw them a little faster because momentum is
Momentum is
conserved.
conserved. Yeah,
That's what I thought, but I don't want to be the one singled
The math
out.
changes too, guys.
no, that doesn't matter.
Yes, it does. Math.
Can we get a motion sensor on this?
Yeah, go get the motion sensor.
Wait,
out.
what do you guys saying?
So guys,
It's
can
not
we
the same.
okay guys, can we conclude
No,
that
do
they
it
go
again,
at the
do it again.
same speed?
No,
No, they're not the same speed.
Slows down.
Yeah, it is.
Have it go a little faster.
Watch. Stop talking.
Go a little
Push
faster.
it! Push it fast!
Oh, it slows down. It slows down.
It slows down.
Slows down.
Yeah, cool.
Slows down.
Yeah.
Oops, Kev.
Man, you're making me don't.
So it does slow down, guys.
I was just making sure you guys.
Yes, physics in your face. It does slow down.
Let's look at your hashtag.
And I liked how Kevin tried different speeds, right? To sample that, he went slow, he went medium, he went
Because some people
fast.
can't, like.
Okay, Kuhn, should you see that?
Yeah, I saw that guy.
Hey, stop bullying my friend.
So, momentum-wise, does the system begin with momentum?
Yes.
Yeah.
Yes. What kind of momentum, positive or negative?
Positive.
Positive, right? Because it's going to the right. Now, after the collision takes place, that total amount of momentum should remain the same. But the only way that's going to be possible is going to be for the speed to be lower because what happened to the mass? It increased. Momentum is mass times velocity. So if momentum is conserved, the product of mass and velocity always has to be the
I'm on
same.
the right track.
And that's the key. Questions? All right, I'm going to stop this. Minutes. I'm going to do it one more time for things.
For video purposes.